In this chapter of the course, we're going to talk about differential equations. So equations that involve derivatives. We're going to tie back together the applications that we have seen for growth and decay, and we're also going to talk about how we can solve differential equations via the methods that we've actually already seen, as well as new ones. We will derive several applications that should seem familiar, and we will discuss what do we do in case of when we are not able to solve the equation exactly, and how are we able to approximate solutions to these equations using the so-called Euler's method. To start off with, let's give a definition of what is a differential equation. In terms of the equation itself, normally we think of things like x squared is equal to 4, and when we solve it, we produce a number answer, in this case, plus or minus 2. A differential equation is also an equation, but it relates not just a variable in numbers, rather it relates one or more derivatives of some function to the function itself. So in the differential equation, we will be seeing the function and its derivatives. Solving the differential equation, therefore, is not coming up with a number answer, but rather to come up with a function that satisfies the given relationship. Let's start off with probably the easiest function to take a derivative of, y equals e to the x. The question here asks to simply write a differential equation that involves this function. Well, I can take a derivative, and what am I going to get? The derivative of e to the x is just e to the x. And here we go. This in itself already is a differential equation. In order to write it more like the relationship between the derivative of a function and the function itself, I might also notice that this e to the x is my original function, which means that I can rewrite this expression as y prime is equal to y. This, in fact, encapsulates how e to the x relates to its derivative. The derivative of e to the x is itself. This differential equation describes the behavior of this function and its derivative. Now, e to the x is a really nice function, so I can in fact extend this out even further. I know that the second derivative of this function will still just be itself. I also know that the second derivative will be the same as the first derivative, and I can come up with lots of differential equations that involve this particular function. All of these are what we call a differential equation. And once again, the solution to it is the function that satisfies it, not a number. Let's take a look and see if we are given a function and a differential equation, how can we determine whether or not this function in fact satisfies this differential equation? There are a number of ways to proceed. You can take a derivative and then you can plug in the function itself and see if the equality actually holds, or you can try to derive an equation and see if your derived equation matches the one provided. So let's start either way by taking the derivative of this function. So it's e to power 3x, which means that the derivative is itself times the derivative of the inside. And then, of course, I notice that this e to the 3x is my original function. So I can replace this with my original function y, which will then give me that y prime is equal to y times 3, or 3 times y, which is exactly the equation given here. So yes, this function, in fact, satisfies this equation. So, in other words, this function is a solution to this differential equation. Now, solutions are usually something that's fairly special. So on the last slide, we saw one function and one of its solutions. Let's take a look at this general equation, dy by dt equals ky, and let's test which ones of these functions are the solutions to this and which ones are not. In other words, which of these functions satisfy this equation? Which of them make it actually equal? So we'll start off with the simplest one, y equals e to the power of kt, and we'll do the exact same process we did before. So first of all, I'm going to take a derivative of my y here, and then plug this or compare this to this equation here to see if it actually works. So t is the variable in this case. The derivative of e to the kt is just itself, and then I have to follow up with the chain rule, multiplying by the derivative of the inside, which is k. So what I notice here, of course, is that e to the kt is exactly my original function. So this is just y, And therefore, I get equation y prime equals to y times k, which is exactly what this equation is saying. I can, of course, rewrite this in the prime form as well, just to make it easier if we're going to use the prime notation throughout. So this function satisfies this equation. Okay, let's put a check mark next to it. And let's try the next one. So what we have here is basically the exact same function, but with a constant. So I'm going to go through the exact same process again. I'm going to take the derivative of this function. Let me write this all the way over here. So in the differentiation rules, I keep the constant and then take a derivative of the function. Now the derivative of e to power kt is simply itself, and then I have to follow up with a chain rule, so times k. And then I'm going to do the same as before. I'm going to compare my derivative to the original. And I'm going to notice that this 5e to kt is exactly my original function. So once again, this is my y, and I can see that the differential equation I get then is y prime equals to y times k, exactly as the equation that I'm asked to check whether it's a solution of. So this function also is the solution to this equation. I can do the exact same thing here, and I'll notice the exact same pattern happening. The derivative here is going to be the function itself times the chain rule that suggests the constant of k. So once again, I get the exact same pattern, and this function also satisfies this exact same equation. So what we notice is that there's something very in common with these three functions. Each one of them has this e to the power of kt, and the constant doesn't actually make a difference to whether this equation is satisfied or not. All of these functions are, in fact, solutions to this equation. Now let's try to play around with it. What if we add a negative into the power? Will this relationship still hold? So let's take a derivative of this guy here. What am I going to have? I'm going to have the derivative of itself or the derivative of e to power anything is itself, times the derivative of the inside, which in this case is minus k. So let's see here. I have that this is my original function, so I can replace this with y. And so the equation I get then is y prime is equal to y times minus k. Well, that doesn't match this equation exactly. I get minus here and no minus here. So this is not the same equation. This function does not satisfy the above differential equation. So the change in the exponent makes a difference. What about if we take a function that's not even an exponential? Can this possibly satisfy this equation? Well, let's take a derivative of this one. If k is a constant, then the derivative of it is just 0, which means that the derivative of it cannot possibly be the constant times the original, so this function does not satisfy the differential equation. And you can go through the rest of them to see, I'm going to leave this as an exercise to you, that none of these actually satisfy the above differential equation. This differential equation is very closely connected to exponential functions with the constant being anything at all you want. In fact, this differential equation describes one of the most characteristic properties of an exponential function, the fact that its rate of growth is proportional to the original. That's what makes this differential equation and exponential functions connected to each other. Now, we can generalize this process and in general talk about which functions satisfy this particular equation that we're going to work with quite a bit throughout the course. So notice here that I have rewritten my equation in the dy by dt form, but I can also work with it in the y prime form. Y prime is equal to ky. What the result is saying is that the solutions to this equation are exactly the exponential functions where k appears as the constant in the actual exponential, and this number c up in the front, being just a constant, can be about just about anything at all. Let's check to make sure, just like in the previous example, that this equation is in fact satisfied by these functions. So I'm going to take the derivative of my function here, Now, in taking the derivative, first of all, I notice that I have the constant c. By the constant multiple rule, I can leave it alone and then take the derivative of what's remaining. What's remaining is e to power kt, so the derivative is itself times the derivative of the inside, which is the power, so the derivative is going to be k. And then, of course, I notice that this ce to power kt is the exact same as my original expression for my function, so this is, in fact, just equal to y, and yes, I get that y prime is equal to k times y, which is what this actual result states. What is actually a stronger result that we're not going to prove is that while these are the solutions to this equation, these are the only solutions to this equation, which means that if I have a differential equation like this, the only functions that satisfy these are the functions of the exponential form. Okay? Nothing else will satisfy this differential equation. So 2 important notes to highlight once again. Solutions to differential equations are functions, not numbers. So you're after an actual function of certain form. And the solutions, of course, depend, being written in this format, will depend on the values of c and the values of k. And we will get a number of different scenarios occurring. So for example, and we've seen this before, if k is positive, so here the exponent is a positive number, or in the differential equation here, the rate of change is therefore positive. What we get is, of course, a positive or a growing, increasing exponential function, which means that generally we'll get exponential growth. What that means, for example, on the graph is if we sketch it, we get a function that we expect to increase and therefore look like this. This is when c is positive. What happens if c is negative? Now, this is not likely to happen in real-life applications, but for mathematical completeness, let's consider that case. If c is negative, I'm going to get the exponential function, but with a negative in front of it, which means that everything gets negated. So what I actually have is the graph that looks like this. Okay? What about the case when k is negative? Well, if k is negative, what I have here is the negative power in the exponent, which means I generally get exponential decay. And again, we can have 2 different cases for the various values of c. The positive value of c is the one that is a more familiar exponential decay that looks like this. And the negative value of c, once again, is not going to be a terribly useful property to have in the realistic applications. But again, just for mathematical completeness, I'm going to include this here. The collection of these curves, because we're getting really a whole collection, right? Depending on the value of c, I might have this, or this, or this, or that, or any other of the infinitely many possibilities. The collection of similar curves is called a family of curves. So in fact, what I have here is a family of solutions. Without specifying what c and k are, my solutions are an entire set of related and similarly shaped curves. If I would like to pick a specific member of this family, I need further information. In particular, if I have some kind of knowledge about the value of c, then if I have infinitely many of these related curves, just fixing one point will allow me to fix the one particular member of the family of solutions that I have to consider. The problems like that are what we call initial value problems, and that is when you have a particular value that is specified at some point. Generally, in real-life situations, you will have the value that is specified at 0, the starting point, so to speak, a real initial value, but this does not need to be the case. You could have a specified point that does not happen at t equals 0, but happens somewhere else, and the process will not actually change. The process of finding a solution will not actually change. Okay, so let's go through this one. What do we have here? We're asked to find the solution to this equation, which again I can rewrite in the prime form if it's a little bit easier on the eye. And I also know that I have this particular point that my solution has to actually contain. Now, in general, from the previous slide, what I know is that the solutions to the equation y equals ky are family of solutions of the form y equals ce to power kt. So let me record that here and then try to match to what I actually have. So the solutions to y prime equals ky are y is equal to ce to power kt. What I have here is I need a solution to y prime equals 5y. So what I immediately notice, of course, is that it means that in my case, k is simply equal to 5. So now, matching this to the solution provided is going to give me the fact that my solution is going to be c e to power 5t. Right? What I have here is k is equal to 5 in this case. Now, the nice thing about the differential equations is that you can always check to make sure whether or not you're doing your arithmetic or sort of this matching game correctly. You could take the derivative of this guy and make sure that it actually satisfies this equation once again. Now, what I have here is almost a perfectly good solution, except for I still don't know the value of c. This is where the initial value will come in handy. I'm going to plug this information into my equation and solve for c. So what am I going to have? My initial value says that at t equals 0, y is equal to 3. So y value itself is equal to 3, which will be the left-hand side here. And this is the case for when t is equal to 0. So that's going to go into my right-hand side. c e to power 5 times 0. 5 times 0 is just 0, so what I actually get from here is that 3 is simply equal to c, which means that overall my solution is y equals to 3, this would be my c, e to power 5t. And what of course you just noticed too is that whenever I plug in 0, this power will be 0, which means that this entire thing will be equal to 1. So I will always have that c is equal to the value at time equals 0, which is why in general we actually have a notation for it. In general, y of 0 is what we call y naught, the starting value, and then solution is, or can be written as, y equals y naught e to power k t. So instead of writing this c down, that might or might not be the actual value at 0, I know that if I have the value at 0, that is simply the constant in front of my equation. Now, as usual, you have to be careful when working out or deriving some kind of laws or rules. Notice that here we have derived a rule for solutions to the equation of the form y prime equals ky. So the derivative of a function is proportional to the function itself. And that is the equation of this form. If the differential equation to begin with is not of this form, we're not going to be able to apply this formula, and therefore we'll have to work out some alternative methods. So let's take a look at the next few examples here and see how we can attack these using the tools and techniques we've seen in the course. So here I have the first one. The solution to the differential equation dy by dt is 5t, given that y naught is equal to 3. So you notice that the shape of the actual differential equation looks very similar to the previous one, where we had dy by dt is equal to 5y, but of course the variable on the right-hand side is different. For the second equation here, the one on the previous slide, we have derived a formula, but it does not apply to this case because this is t, the derivative, the variable that I'm taking the derivative with respect to, not the variable that I'm taking the derivative of. And that is a very important distinction. So let's rewrite this in the prime notation to see if this will trigger any kind of memories of the concepts that we've seen previously in the course. So what I have here is the derivative of the function is equal to 5t, and t is in fact my independent variable. So I have to think about this here. What function did I have to take a derivative of to get 5t? This is only dependent on t, or your x if you prefer x as your variable of choice. So I can apply anti-differentiation rules that we have seen halfway through the semester. What function did I have to take a derivative of to get 5t? I can simply apply anti-differentiation rules, if you recall them. This was a while back now. And I can leave the constant alone and then apply the anti-power rule to this t. So it will produce t squared over 2. And remember that the nice thing about anti-differentiation is the fact that you can always check it by taking the derivative. If I take this expression now and take derivative of both left and right-hand side, what am I going to get? Well, on the left-hand side, I'm going to get y prime, and on the right-hand side, I'm going to have to apply the power rule. So I'm going to leave the constant alone. It's going to travel here. 2 is going to come down and get canceled out with this 2, and I'm in good shape here. The only other thing that you have to remember is the fact that derivatives are not unique. So I have to follow this up by a constant, right? If I take a derivative of this expression with any constant attached here, I am going to have the function that I'm after. So I have to make sure that I include that constant to point out that this, once again, is an entire family of functions that satisfies this differential equation. And that is when the initial condition is going to come in handy. I'm going to plug this in here and be able to figure out the value for c. So if I plug this in, y of naught is 3, so my left-hand side is 3, and my t on the right-hand side is 0, which gives me that c is equal to 3, because this entire part is going to be equal to 0. I plug c in here, and that is my final answer. So what I'm going to have is, for this initial value problem, the answer is 5t squared over 2 plus 3. So notice the difference between this approach and the one on the previous page. Here, we were able to actually take the antiderivative because the right-hand side is given completely in terms of the independent variable t. On the previous page, we needed to develop new methods because we cannot take antiderivatives when the function on the right-hand side is the one that we're taking the derivative of itself. So, looking at this new exercise, the next one up, we see the same pattern as here. dy by dt is 5t squared plus 4. So the right-hand side is given fully in terms of my independent variable t, which means that I can apply my anti-differentiation rules. Take a minute here, pause the video, and try to actually work this out for yourself. So what I'm going to have here is my function, and then I'm going to apply the anti-power rules here. So I'm going to have 5t cubed over 3 plus 4t as the function, plus the constant that I'm going to determine using my initial condition. So the initial condition says y of naught is equal to 3. So y is equal to 3 while t is equal to 0. So I'm going to have here this equation for solving c. And as before, this is also very simple. Both of these are going to turn into 0, and c will once again turn out to be 3. Now, it's not always the case that this is exactly going to be the value for my c. So I probably should have picked an example that showcases that. But here, we ended up with both of the same constant by accident, and this is my full solution. Okay, so in the case of initial value problems, if you are only given the function, then you're only going to be able to produce the answer up to the constant. If you're given the initial condition, you're able to use that initial condition to solve for that constant. And now let's take a look at our first application. That is the model for population growth. Generally, the size of a population depends on numerous processes. For our first model, we're going to make a bunch of simplifying assumptions so we can carry out our very first calculations. First of all, we're going to assume what we call system being closed, and that means that there's no immigration and then there's no emigration. So whatever happens to the population happens to the population sort of inside, very pandemic-like. We're also going to assume that birth rates are proportional to population size. So if my population is denoted by P, then I'm going to assume that the rate of births is equal to some constant B times the population size. So we're assuming some proportion of the population is actually be giving births to other humans or other species, I suppose. We're going to assume something very similar about death rates. We're also going to assume that they are proportional to the population size. Again, this is our very first model, so it does have simplifying assumptions. More realistic population models will involve the fact that, for example, death rates are density dependent. The denser the population, the higher death rates actually are. Now, with these ones, if these are the only processes that affect the population, then we can fairly quickly think about what actually then happens to the rate of change of population as a whole. What affects it? Well, first of all, of course, the rate of change means that I have to account for positive changes, which is the rate of births. This is what adds to the population. And then I have to take away the negative changes. So the rate of deaths that happens in the population. Now, this entire equation is based on rates of, which means that this in itself is a differential equation. The rate of change of population is the derivative of the population with respect to time. The rate of births being proportional to the population size is just BP. The rate of deaths is dP, where B and D are some kind of birth and mortality constants. Now I can see that I can simplify this a little bit because I can actually factor P out on the right-hand side. So what I have is dP by dt is equal to B minus D times P. Or, again, if you prefer the prime notation, P prime equals to B minus D times P. You can already see how this is similar to the equation that we've just talked about of y prime equals ky, except for my constant k here is composed of two other constants. But this should not affect how I actually proceed to calculate the solution. Let's take a look at real Canadian population data. We're going to take Census 2000 data as our initial point for model construction. The population size calculated in that census or collected from the actual Canadian population was 30,689,000 people, approximately. I narrowed it down to the closest thousand. So this is our initial population. We're going to call it P0 or P0. Next, we are given birth rate and death rate in per capita units. So that means that these are already your proportional constants. So as per the last slide, this will correspond to the constant B, and this will correspond to the constant D. So once again, note that because they're given per capita, I don't need to do any division. If I was given the number of births and the number of deaths, then I will actually have to figure out the rate. In this case, it was already computed for me. So it seems, again, as per the last slide, I have all the necessary pieces in order to construct my model from scratch. So the model itself is going to be that P prime, so the rate of change of the population, is the birth rate minus the death rate times the population size. Now, I actually have numbers here that I can plug in into my model. So I can take the values for B and D and plug them into here in order to get B prime is equal to, I'm going to do a little arithmetic on the side here in order to figure out what B minus D actually is in as a decimal. And I'm going to end up with B minus D, so this number minus this number is 0.0036. So this is fantastic news. I already have my model, but before we move on to talk about the solution to it, it is important to make certain observations, at least to figure out if what we have makes sense in terms of our context. So take a look at this number here, 0.0036. One very important thing to notice about this number is that it is positive, which means that the population is actually increasing. Now, this is important for several reasons. It's important if, in case we decide to actually use this model to predict future numbers, knowing that the current the current formula suggests that the population is increasing. If I now use 2000 data to predict 2024 data, I am expecting the number to be larger than the initial population I started with. And if I end up with a number that is smaller than that, I know I went astray somewhere. So building expectations is very important. I also noticed that the birth rate is in fact a bigger number than the death rate. So if somehow in my arithmetic this ended up being negative, I know that I typed something wrong into my calculator. Now, the nice thing about this equation, of course, is that it's of the form p prime or y prime is equal to ky, which means that I know exactly what the solution to this will be, which would be y equals to y naught e to the power of kt. So notice how my constant in front of the y, or in our case p, if that's what we're going to call it, travels up to the exponent in the solution. So I suggest pausing the video here and maybe trying to write down the actual solution yourself, just in order to be able to practice a little bit more with the different variable names. But overall, your solution should end up being p naught e to the power 0.0036 t. So notice again how this constant simply travels up to the exponent for the e number. Now, I actually know my initial population size that is coming out of the census data from 2000. So I'm going to have 30,689,000 people times e to power 0.0036 t. Now, this is in fact fantastic news because now I have an immediate solution to the population size at any given time t after 2000. Now, notice that because I set this to be t equals to 0, if I'm going to be computing the number for 2024, my t is not going to be 2024, it's actually going to be 24. Okay, important to keep in mind, otherwise you're going to get numbers that are way too big for what you actually should be calculating. So for year 2024, I'm actually plugging 24 in for t. So let me rewrite this entire number. E to power 0.0036 times 24. And again, doing arithmetic on the side, I am going to round the number of people that I'm getting, but my number here is 33,458,000 and 446 people. Now, of course, I'm computing with people, so I'm going to round it down to something. It is sort of my choice, up to me here. I've rounded up to the nearest human. Please don't have decimal humans. That is not very realistic. Now, what do we have here in the end? What we have just computed is, given the census data from 2000, the birth and death rate of the Canadian population in year 2000, we've computed the model that can be used to calculate the population sizes in the future years. And in particular, we have calculated the population size for the year 2024, which is where we are here today. Now, of course, this is not going to be exact, and we don't expect it to be very close even to the reality, because 2024 is quite the ways away from 2000. And the further away we move from the initial point where we set up the model, the more inaccurate the model becomes. But just how inaccurate? Well, luckily for us, we do have a variety of different tools and data collection mechanisms to see what the actual population of Canada is right now. So there's this website that is available through Statistics Canada that shows in real time the modeling of the Canadian population. So right now in October of 2024, this is saying that the Canadian population is nearly 42 million, 41,772,000. Now that's quite a ways away from the number that we computed, because that was 33 million. So let's talk a little bit about what is the discrepancy about. First of all, our model was very simple. All we accounted for was births and deaths. And as you can see on your screen right now, this model, the more realistic, complex model, accounts for births, deaths, immigration, emigration. Non-permanent and interprovincial migrants do not add to the overall population, but just are moving around provinces. Now, this model actually does the per province and territory distribution here, and you can see in real time, it's actually modeling the movement inside the country as well as coming in and out of the country. This model, as opposed to ours, is much more complex. And if you click on the related products and notes here, you will see just how many different data points it's actually continuously ingesting in order to build and adjust the processes. We can also see at the very bottom of this website, it says that the last date modified was September 25th of 2024, which means that this is the last time that the model was probably reset and changed up. It has to be close enough from the point of being built to the point where the prediction is made for the predictions to be realistic. So again, our predictions with our very simple model were a huge underestimate, right? The real Canadian population right now is over 41 million, whereas what we've computed was just over 33 million. There's many things that are accounting for it. Maybe the birth rate in 2000 was much lower than the birth rate now. Maybe the death rate was too high. Maybe we've had a lot more immigration since COVID, and so on and so forth. There is many different variables that go into model construction, and they need to be thought of in terms of the context every single time you apply a model to predict anything in the future. Look at the two other ways that we can describe population growth and radioactive decay. And these are the concepts of half-life and doubling time, each corresponding to whether the function is that of growth or of decay. On this slide, we're going to see how those two concepts are actually similar. So for population growth, we have a differential equation that states that the rate of growth is proportional to the size of the population. If we're talking about the growth, then this constant of proportionality is going to be positive. And if the population is growing, then we can of course discuss things like doubling time, meaning when is the population going to be twice the size that it started with? So as a first step, we're going to transform the differential equation into the equation for population growth or into its solution. So what I have here is that the population size is equal to the initial population times e to the power of the constant of growth times the time. Okay, now again, if I'm interested in the doubling time, that means that if I started with P naught, I would like to know at which point the population size is going to be twice the initial. So the population size I'm after is twice P naught, and I want to know when does that equal to the population at this time. So I'm trying to solve for t here, k being some sort of constant. First of all, I'm not starting with the zero population, so I can divide both sides by p naught and cancel those out. And then the next equation I'm going to have is 2 equals e to power kt. I can take logarithms of both sides and then use the logarithmic rules on the right-hand side to simplify the expression here. And so what I have is ln 2 is equal to kt, and again, k being a constant, I am solving for t here, which comes out to be ln 2 divided by k. So this, if you know the constant of growth, this is the time at which the initial population will double. On the flip side, let's discuss the radioactive decay. So the differential equation for it here is stating that the rate at which the radioactive material decays is negatively proportional to the amount of material left. Now, in order to explicitly state that it's negatively proportional, I am going to insist on including this minus here, and then to ensure that this quantity is in fact negative, I actually have to state that k itself is positive. Because if this was negative inside, the negative of a negative would have produced a positive number. By explicitly including the minus, I have to ensure that the constant itself stays positive. Now, we're going to follow a very similar process, but for a new equation here. So first things first, I'm going to turn this differential equation into the actual solution. So what I have is the amount of radioactive material is the initial amount times e to the power of the constant of decay, which is minus k times the time. And because it's decaying, I'm interested in half-life. So the amount of time that passes before I have exactly half the amount of material left. If I start with R naught, that means I'm interested in the value for t at which there's exactly half of R naught left. So my equation here is going to be half of R naught is equal to R naught e to the negative kt. Again, I can actually divide both sides by R naught, assuming that it's not negative, and my next equation is going to be 1/2 is equal to e to the power of negative kt. I can take logarithm of both sides, and what I will have is ln of 1/2 is equal to minus kt. Now, I can solve for t here, but I can also simplify this expression a little bit by realizing that ln of 1/2 is the same as negative ln of 2. And then my equation will turn into negative ln 2 is equal to negative kt. Pause the video for a second just to persuade yourself that these two quantities are actually the same. You can pull out a calculator and calculate this first and note that that is in fact the case, or you can really go through the simplifications following the logarithmic rules to practice them a little bit more. Now, looking at this equation here, I notice that there's minus on both sides, so I can cancel that out, turning this into ln of 2 equals 2 kt, and then solving for t, I have ln of 2 divided by k. Now, note that the surprising thing is that both of these are actually exactly the same. So if I insist on keeping the constant positive and including a separate minus, then the concept of half-life in the radioactive decay is very analogous to the concept of doubling time in the population growth example, to the point where the way to calculate them is going to lead to the exact same formula. Now, once we have derived the formula, we can actually use the formula directly. So if you have a question that's asking for doubling time or half-life, you can of course go through the setup process and find the time this way, or if you have the formula on hand, you can simply call upon the formula to help you solve the question a little bit more efficiently. Let's take a look at an application of how to use these formulas in the specific setup. So the specific setup I'm going to use is that of the Chernobyl disaster, on which we have lots of data by now. And it's actually personally important to me because everybody is aware that Chernobyl happened in Ukraine. Very few people are aware that Chernobyl actually happened on the border between Ukraine and Belarus. And I happen to be exactly from Belarus, from Minsk, just about here. So let's take a look at some of the data that we have from there. The Chernobyl disaster happened in 1986. And it released in particular large quantities of iodine-131 and cesium-137. These two elements are well studied in a lab, and therefore we actually know their half-lives. Iodine-131 has a half-life of 8 days, so very short half-life, whereas cesium-137 has a half-life of 30 years, which will bring us to about this time right now. What we're wondering is how much of these materials actually remain present today. I'm going to solve this problem for iodine-131, and I encourage you to actually do this for cesium-137. So what do I have in terms of the equation for iodine-131? I know that it decays exponentially, so I'm going to assume that it decays simply exponentially, which means that it follows the exact equation I had on the previous slide that says that the rate of the decay is negatively proportional to the amount of material present. What I don't know yet is I am given what the half-life is, but I don't actually know what this constant k is equal to. So this will be my first order of business, finding k. I can set up the equation from scratch again, but what I'm going to do is actually use what we have derived on the last slide. So from the last slide, what we found out is if I set up the equation this way, explicitly including the minus here, is that, let's take a look, that t, the half-life, is equal to ln of 2 equals to k. Now, I can actually solve this equation the other way around for K instead of T. In this case, I know the half-life and I need to know the K, so this equation will be useful if it's solved for K instead of T. And I can note that this will give me that K is equal to ln 2 divided by T. Now, we have to decide what are the units of time that we're going to use. The half-life of iodine is given in days, but our timeline is sort of given in years, and I would like to know how much there's present today, which is more than 30 years from then, so I have to decide whether it is days I'm going to use or years. I'm going to use years, which means that first of all, I have to convert 8 days into years. I'm going to skip the calculations for that and include simply a number. 8 days in years is 0.021917. So let me note here that this is 8 days in years. Now, if I simply calculate this number as a K, it turns out to be approximately 31.626. So that gives me that I can plug this as the value of K into my model. So overall, I have that dr by dt is equal to negative 31.626 of r. Okay, again, just common sense, quick common sense check that this is negative, meaning that this is in fact a decay, and we are in good shape. This is the differential equation. I would like to know exactly how much material still remains today, so I am after the solution here. Again, recalling that the solution will give me the amount present today is equal to the initial amount, e to the power of the constant, so minus 31.626 t, which means that I can now calculate the current amount by simply plugging in the value for t at which I'm interested. Now again, because I've decided that I'm going to use years as units, I simply have to calculate years of that have passed since 1986, and that is in 2021 going to be 35 years. I'm going to plug 35 in for t here. Let me write this out. So I'm going to have r naught e to power minus 31.626 times 35 years. And then you can plug this into your calculator to figure out what constant this actually gives you, or what number it actually gives you. And you're going to notice that this gives you 0. Well, is this something that we actually expect to have happened? That there is almost no, or in limit, no amount of iodine 131 left? Yes, I think that makes perfect sense. If the half-life is 8 days, that means that every 8 days, half of the material goes away, and it has been 35 years worth of time that passed between then and now, which means that by now, there's none of the iodine 131 left. You can also, I'm not going to go through the calculations, I'm going to leave the calculations for cesium-137 to you, but you can also establish an expectation of what you expect your answer to be there. The half-life of cesium is 30 years, and it's been 35 years since then. So what you expect is to see the initial number times approximately a half, because by now, approximately a half, just over a half of cesium-137 would have actually decayed in the ecosystem. In this next example, we're going to consider general setup for organismal growth. We will have to make some simplifying assumptions along the way, but this is going to be generally a reasonable approach to think about how cells grow. We're going to start with a cubic cell, just so that we can have a handle on the shape of the cell, with side length L and mass M. So altogether, what we're thinking about, just so we have all the same picture in our heads, is a cube of side length L. Now, I am interested in the mass of the cell, and in fact, what I would really like to know is how does the mass change as the side length changes and the entire cell grows? So first, I would like some kind of relationship between the mass and the size of the cell. Now, one such relationship is given by density times volume being equal to the mass. Okay, if the cell is little, then I can assume that density is uniform throughout and therefore constant. So let's assign some kind of constant to the density. Let's call it d. And in terms of volume, if I have a cube of side length L, then I know that the volume is going to be L times L times L, or L cubed. So altogether, from this equation, I have that my mass is equal to some density constant times L cubed for the volume of the cell. If I'm interested in how these things are related to each other as the cell grows, I am interested in the derivative of this expression taken with respect to time. So I'm going to recall how we actually take derivatives with respect to time of all the things that change with respect to time. And remember concepts, or rather techniques, such as related rates problems. I'm going to take a derivative of this entire equation as stated. Keep it in mind that everything is dependent on time. So mass, as it changes with respect to time, will produce a derivative of dm by dt. On the right-hand side, if I take a derivative with respect to time, the density is a constant, so it will stay put, and then I have to take a derivative of L cubed. According to the chain rule, I first take the derivative of the outside function, which is the cube here, so 3L squared, and then I have to follow up by the derivative of the inside, which is L itself, which itself will change with time, so this will be followed up by the derivative of dl by dt. I don't know it explicitly, but I don't have to. I will simply think of it as an expression of the rate of change of the side length with respect to time. Now, what I'm actually going to do is derive the expression for dm by dt, the change in mass with time, in a different way. So let's take a look at some biological processes that occur within the cell. The cell ingests food at the rate proportional to its surface area, and that is because it ingests food by allowing it to permeate through the membranes from the outside. Now, that means that I have some sort of proportionality constant times the surface area. The surface area of the cube are going to be all of the faces of the cube, each one of which has area of L squared. Now, there are 6 of them, but I also have the proportionality constant for the ingestion, so I'm going to call this proportionality constant S, and so the whole thing is going to be proportional to SL squared. Again, I know that there's 6 faces of the cube, but I already have the proportionality constant here, so this 6 got basically absorbed into the proportionality constant S. On the other hand, the cell consumes food at the rate proportional to its volume. It has to actually sustain life throughout the entire cell, so it's proportional to the volume. I'm going to call the proportionality constant here V, and the volume, as discussed before, is actually L cubed. Now, that means that the cell's mass changes with absorption of nutrients and consumption of nutrients. Absorption, of course, affects the actual mass positively. It adds to the mass, whereas the consumption is something that we have to subtract because this is what cell needs to consume to live, and therefore the nutrients actually go away and do not make cell larger. Now, luckily for us, absorption and consumption are exactly the things that we have just derived, so we can plug them in. Absorption is going to be SL squared, and consumption is going to be VL cubed. Now, what we're going to remember is that we actually already derived an expression for dm by dt. Here it is. So these have to describe the same exact phenomenon. Therefore, the 2 expressions for it can be set to be equal, and then we can see what else inside of this we can solve for. So what I'm going to do is simply take this expression and rewrite this in the equation together with the new way to describe the dm by dt that I have just come up with. So all I have here then is an equation that connects quite a few of the variables. Now recall that S, V, and D are simply constants of proportionality, whether density or volume or surface area proportionality. And so in terms of my unknowns, I have the length of the side of the cube and how fast that grows. We're going to use this to solve for dl by dt. So let's make a note here. I'd like to solve for dl by dt. I encourage you to pause the video for a second and actually try to solve this equation for dl by dt, keeping in mind that you're essentially going to treat everything else as constant for now. You're going to isolate dl by dt and then simplify the expression as much as you can. Pause the video, see if you can do it. The expression we should get for dl by dt in this case is going to be SL squared minus VL cubed, the entire right-hand side here, divided by the coefficient in front of my dl by dt. So divided by d times 3L squared. What I'm going to do next is actually simplify this expression a little bit. I know that this is a lot of constant and sometimes can be kind of difficult to stare at, but bear with me here, we're almost there. So what I'm going to do is basically undo the common denominators with this minus. I have this fraction here minus this other fraction here. So let's take it a little bit slowly. I have SL squared over d times 3L squared minus VL cubed divided by d times 3L squared. And now I can notice that I can actually simplify things quite a bit, right? For example, L squares here will cancel out. L will cancel out, a number of L's will cancel out here. So what I have altogether in a simplified version is S divided by 3D minus V divided by 3D times L, right? So all of the L's got canceled here, but I still have one L remaining here. This is a constant because this is just the surface proportionality constant and the density, and this is also a constant for the exact same reasons. So let's give these guys names. Let's say we'll call this K1 and we'll call this K2. So I can rewrite this expression in a slightly more pleasing way without too many constants. K1 minus K2L. So what we have here is the equation dl by dt is equal to K1 minus K2L. So this is saying that the rate of growth of the side length is negatively proportional to the side length itself with some other constant added to it. Note that this equation is not the same as the basic time that we've been solving so far, where I have, for example, dp by dt is equal to kp. There is more to it on the right-hand side here. So this is a new equation for us, and we're going to have to come up with a new solution to something like this. And this is another topic that we're going to consider for the next class. The last thing in this lecture, let's simply think about how we can set up differential equations for different scenarios and where we will see the different types of equations. So here we have the population grows at an annual rate of 1.25%. So this is saying that the population growth is proportional to the current population size with a proportionality rate of 1.25%. So the differential equation will be the proportionality or the rate of growth of the population is proportional with the proportionality constant of 1.25%. Remember, percent means divided by 100 times the size of the population itself. The next one, radioactive sample loses 5.6% of its mass every day. So in terms of the differential equation, that means that I have a negative proportionality constant of minus 0.056. And the corresponding differential equation then is going to be minus 0.056 of R, right? Again, recall that this is saying that the rate at which the material decays is negatively proportional with this constant to the amount of material still present. The next example is a bit more complicated because there's two pieces of information we have to keep in mind. Your bank account earns 4% of interest every year, which is very similar to our first problem here, It's 4% of whatever you have in the account. So I can start setting up my equation. Let's say the amount of money is going to be A. So the rate at which it grows is proportional with 4% proportionality to the amount of money I have in the account already. However, I still have a second sentence to go here. At the same time, you withdraw money from the account at the rate of $1,000 per year. Notice that this 1,000 is not proportional to whatever you have in the amount in the bank account already, right? So whether you have 2,000 there or 2 million there, you're going to withdraw $1,000. 4% relates particularly to the amount you already have in the account. $1,000 is simply a constant withdrawal. So the rate of change of the money in your account depends 4% on what you earn with interest minus $1,000 that is a constant by itself, does not get multiplied by A because it is completely independent of whatever else you have in the account. And here, you notice the exact same type of equation that we have just seen with the organismal growth. You have a part that is proportional to the amount that's present, and you have a constant part that does not depend on that. And again, whereas the first two equations are something we have solutions for, this last one is something we're going to have to examine a little bit closer. Let's take a little last example here, which is particularly relevant to our pandemic situation we're all in right now. This is a well-known principle of how epidemics actually spread. The rate at which an epidemic spreads is proportional to the product of the number of people who have caught the disease and the number of people who have not. So this is a key word here. It's proportional to the product. Let's think about what does that first of all mean for the epidemic to spread. Epidemic spreads, meaning that the number of infected individuals changes or increases. So we're going to have to think of the individuals that are infected or the ones that have already caught the disease. Let's call this group infected and label them with a variable I. And we also have the people who have not yet caught the disease. These we're going to call susceptible because they're susceptible to the disease. This is the vaccine-free scenario for now, and we're going to call them S. So now what we have is that the way the epidemic spreads, the rate at which it spreads, so the rate at which the infected individuals, the number of infected individuals grow, is proportional, so I have the constant of proportionality, to the product of the number of infected individuals and the number of susceptible ones. So proportional to I times S. So these two types of equations are new and not something we have solutions for yet. This one we will study in a couple of lectures, but this one is not something that is within the scope of this course. If you're interested in how the epidemics spread and how the products of the differential equations work, you should consider taking Math 118, which is Calculus 2 for Life Sciences, where all of these equations and this one will be studied in a lot more detail.